Obviously, we need to go to the real world and show that geostrophic balance does work at large scale, right? So here is our familiar figure from chapter 5, where we had shown geopotential height as deviations from the averages at each pressure surface. So this is annual mean, and these are deviations at this particular height. So negative means below the annual mean and positive means above the annual mean. So you have positive geopotential height here compared to the annual mean. So geopotential surface is domed over there and dropping off. As we said, we looked at 500 millibar, for example, went from 5.8 kilometers down to about 5 kilometers. So it dropped by about 900 meters, right? From the tropics to higher latitudes. So that's kind of what's happening here. So you can estimate the strengths of wind here to see if in fact the geopotential height anomalies correspond to the geostrophic balance. So remembering that geostrophic winds are G over F dz dy, right? So dz dy, the geopotential height gradient in the y direction is going to give us zonal geostrophic wind. So you plug in the approximate values for the dimension, the scales that we see here. That's typical. So 9.81 divided by 10 to the minus 4 at some particular latitude times a drop of 800 meters over 50,000 kilometers, right? 50,000, 5 times 10 to the 6 meters. That gives us a value of geostrophic wind of 15 meter per second. So if you go and look at our wind distribution, again the zonal mean meridional section, this time looking at annual mean, DJF and JJA. So you should get used to these terminologies, DJF and JJA, MAM, SOM. So these are just seasonal means, and if you just say DJF, JJA, you will sound like an expert, right? So we had weak easterlies in the tropics, and then we had this zonal winds that were increasing from the surface to the height, and they had a seasonality where the winter hemisphere had the strongest jet stream, and you can see that DJF is the northern hemisphere winter, JJA is the southern hemisphere winter. So you can see that winds are jet stream is weaker here, stronger here, weaker here, stronger here, and so on. So we are looking for this relation between the geopotential height gradient and the geostrophic velocity, which approximately works order 15 meter per second, corresponding to the gradient in the geopotential height in the meridional direction. What does that mean? That means on large scales, indeed, there is a strong geostrophic balance between the geopotential height in the zonal mean meridional sense and the zonal winds in the zonal mean meridional sense. Okay, so we'll keep visiting this in many different contexts. So here is again our 500 millibar height analysis. We were going from the tropics 5.88 kilometers down to about 4.9 or so. You look at a particular section, 7.4. So this is from 5th chapter. This is from the 7th chapter. We'll repeat these figures. We just looked at this with our low pressure centers, high pressure centers, and so on. And if you look at a section drawn this way, we can look at the highs and lows. These are called synoptic charts. Basically, it's what like a bird's eye view of the weather features. Okay, it's a very common word used by weather people in the atmosphere. Synoptic charts. Typically, they are pressure charts with winds on top. We had already seen that the height contours of the 500 millibar wind geopotential are streamlines of geostrophic flow. So you can plug in our numbers again, and we get 24 meter per second winds, which correspond well with the gradient that we observed. So there is in fact a very close relation. Obviously we go back to our Rossby number, and you can see that over large parts of smooth flow over these contours, okay, this is for a particular day, so you see a lot more eddy like features, lot more small scale low and high pressure centers, whereas when you look at the monthly mean, this is for June, okay, it's the same section here, June 21, 2003. It's just blown up along some section. Okay, so you can see this again for the same day, June 21, 2003. If you compute Rossby number, they are basically small or large parts where we have geostrophic flow along height contours. But when you get close to these low pressure and high pressure centers, Rossby waves go close to 1. Okay, then what does that mean? Obviously geostrophic flow is only valid for small Rossby numbers. Okay, so in that case u dot grad u divided by fu is not small. F times u is not small. So Rossby number has to be small for geostrophic balance, otherwise you're going to have other terms in the equation of motion that are going to be important, like at this point here. Okay, so here you get what is called gradient wind balance. We will see what that means. Basically that means the flow is not along constant pressure lines anymore. It is down the pressure gradient, which is what you intuitively expect, right? High pressure to low pressure. That's what you expect. That's the gradient wind balance. So when you get high Rossby numbers, geostrophic balance is not valid anymore. That's all you have to remember. We're just repeating a couple of things, so just make sure you carry the concepts. Low Rossby number is very critical for geostrophic balance to be a strong constraint. Things are never really in geostrophic balance. You can see there are slight deviations, but it's just a matter of how close to geostrophic balance winds are. As you go above the surface at 500 millibar, where the friction is very less, on synoptic scales, you do get largely geostrophically balanced winds. So obviously geostrophic balance is a strong constraint in the mid-latitudes. As you get closer to the equator, F gets small and Rossby number gets large, but even at mid-latitude, Rossby number gets large when you have these eddies with strong cyclonic or anticyclonic circulations around them. We'll see that that's because the vertical motion is not so small anymore.